And then we're like, okay, we have portable wireless monitors of everything except for these crazy tubes and hoses that we have that are tying us down to our bikes.
Yeah.
And so if we could figure out a way to make that wireless, that's where we need to go. And Peter said his original quote was, "I could build that in a weekend."
So
like,
young and hopeful and foolish.
I was, and I said, if you can build this in a weekend, then we have a business to start. And so, and that was the start of VO2 Master. And fascinatingly, it didn't take him long to build it, because yeah, we can talk a little bit. Peter can talk.
Just a flow sensor and an oxygen sensor and a CO2 sensor. Sometimes, how complicated could it be? So it turns out it's actually really complicated.
Yeah, maybe Peter, take us through your thought process when you got in there. Even maybe let's go back to the data management side of things. How did you first become interested in that? You said you were into computer sciences. So how did you get into the data management side of things, and then how did you progress towards that? You know, figuring out how to build a portable metabolic analyzer in a weekend.
I think it's all really my dad's fault. He's a proper nerd. He was a physics prof at the local university. So at a young age, he bought me a few coding books, even like in elementary school, and was trying to bias me down that path, and it worked. In high school, I just realized how sort of magical it was that you can manipulate technology to do anything. That's sort of you get to see behind the curtain for how every application you've ever used works, and that was just super cool. I was a swimmer for the first 10 years of sort of swimmer up until I was about 15. And then when I got into cycling with Andrew, I just, the devices he was using, each one produced a CSV file. And, none of them talk to each other at all. So you have these doctors, these brilliant people who do a test, and then they spent like 2 hours putting data tables together to make graphs. And that's just crazy. So first tool I made, I essentially, I think, learned how to code in C#.net, and built this little desktop tool for free for them. And it just loaded up the CSV files, and you could, time align them and put on different averages and add some lactate data, and essentially just make those graphs that took away the first hour of manual work. And I think it was just good timing. It was in something I really enjoyed, and it wasn't overly complicated. So I think I was 17 at the time, and I kind of got to see a project from start to finish. So that was a confidence boost. And yeah, how did it get into hardware? I think it was just a really exciting idea. Like, I love the idea of building things that become bigger than myself. You can do something on a computer, you can make some code that does something, but that's not nearly as impactful as like building a scalable solution that can affect hundreds or thousands of people. And maybe that's my core motivator, of now I get to go on Instagram and see these strangers all around the world use a VO2 Master, and that's just, man, I want to like go to Europe one day and just be walking down the road and someone's running by with one of these things on, and I'll just go, oh cool, I did a part of that.
No, that's pretty incredible. What, again, going through your thought process when you started thinking about building it, what for you were the major components, and what were maybe going to be the biggest challenges that you would have had to overcome?
I think the biggest challenges was just having, I guess, the classic startup challenge of not having any resources. Like, fundamentally, you need a way to measure flow and to measure oxygen. And we wanted to make something really simple and small. So you had to eliminate a lot of the sort of the encumbering features of technology that was mostly dated. Like the Cosmed FitMate was an awesome product in 1999 when it came out with a thermal printer that looks like a receipt. So you charge someone $100 for a test, like, here's your receipt. You go, oh, okay, that's, and then it had, an LCD screen and buttons, and yeah, that was awesome in the turn of the millennium. But these aren't difficult things to improve upon. You can take all that away and just put a little Bluetooth chip in it, and that alone would be an enormous improvement. So I think I kind of started there of, well, making it better might not be that difficult. And I actually, at the time, but before this became a full-time gig, I bounced around a bit when I was 18, trying to figure out life. I ended up working in the oil fields. So I'd be setting up scaffolding around like a wellhead in northern Alberta. We'd do an hour of work and then be on standby for hours. So I was in the work truck just playing with oxygen sensors. I could get a little sample kit, hook it up to my computer, and start playing with the partial pressure waveforms. And it was super challenging going from that to a real company. I got lucky getting on board with a local tech group, Accelerate Okanagan, and having some great mentors like Gary Van Soest and Byron Bolton, Lance Schaefer. And I think I just, slowly learned the components needed. The business side was fun to learn. I think the most challenging was having to say like design circuit boards and write code and make plastics with no budget. So thankfully 3D printers were a thing, and some of my friends are going through school for electrical engineering. So I got to sort of get some ideas from them, but it was really, really hard at first. I built the first version. I built everything: circuits, mechanics, firmware, phone app, desktop software for diagnostics. And then I got to slowly like hire people into roles. So kind of before that happened, we got a nice research grant with UBCO. I got to work with Professor Kenneth Chow and gain access to a few students there who helped us design probably the most unique aspect of the VO2 Master, the way it samples gases without a pump, without any moving parts, which makes the power supply small and makes the whole device assemblable on the face. And after that, it was a process of getting the first full-time engineer, and then I think since then it's grown exponentially, and now I just have a ton of fun leading a team of 7 engineers and a sales team, and I think company headcount now is well over 10, and we have 4 open positions. And I get to kind of do what I always did in terms of creativity and ideas, but then I get to delegate to these brilliant people we've hired. And that's just so much fun. You have a weekly meeting, you say, oh, let's try these 10 things. And then, they make it way better than I ever could. And I get to see the idea come back and you iterate on it. And then while they're doing that, I get to, have fun being on podcasts. It's feel like I'm living the dream.
It is pretty great. Andrew, do you remember testing the first model, or one of the early ones?
Yeah, I totally do. It was this crazy. There was 2 things that really stand out, and one of them was this meeting we had at UBCO, is a University of British Columbia in the Okanagan, fairly new campus and Ken Chow is a brilliant engineer who heads their department, and Peter really impressed Ken and the group there, and the funding groups, because he was engaged with the actual development of the students. So we had a bunch of grants that would bring on either a high-level undergrad student or a master's student, and Peter would go down regularly to sit with them and work with them as a partner in the development. And most businesses wouldn't do that. They'd hire a student and let the student do their work term or whatever. But Peter was actually there sharing what he had done up to that point and help the students actually progress from there. And we had one brilliant student named Kyle Halliday that Ken identified as a sort of a next generation brilliance in engineering. And I remember the meeting, we actually pulled it together with a couple of the funding sources who were making decisions about our next level of support, who wanted to sort of see our progress to that point. And so Peter and I went down, Ken was there. There were a couple profs from the physiology department, one from the who was doing a bunch of pediatric research. And then these 2 master students and Kyle Halliday, and Kyle went up to the whiteboard and sort of described what he was doing, and then said, I think I can get rid of the pump. And the room kind of went silent, and he started explaining his theory on how he could move air through our device without actually having to pull it into the oxygen cell. And I kind of said, well, what if that happens? What does that mean for us if that happens? And it was either Ken or Peter said, no moving parts, very little power required to work the device, and way smaller. And I'm like, you just completely changed the device that we had dreamed of and made it, that had done two of the things that we wanted to do, which was make it smaller and make it more portable. It was just like, so he completely changed the direction of our, he changed the, he changed the final product in that single meeting. And that was, it was all the work that Peter had done to get him to that point, and to get him into the room with Ken and the brains into the room to help make the device change in that split second. And it was awesome. So and that secured funding for our next round of, go ahead, Peter.
Yeah, and that was I think patent number 1 of 4 so far. And maybe I could jump in with a brief explanation of like where these different technologies came from. There's lab carts, backpacks, and entirely face-worn devices. So the lab carts, that it's a great idea. It's maybe a bit of an older idea, but still works. Of if you want to measure a gas and flow, you simply put a two-way breathing valve at the face. You take all the exhaled air of the person, you put it down a tube, you put it through a turbine or a pneumotac to measure flow. You mix it in a mixing chamber, so all the gas waveforms of breathing become completely flat. You take a mechanical average.
Can you break that down? Can you break that down for the average person who's interested in all this, but maybe doesn't understand the broader concept yet?
So essentially, you need to know how much flow is going out of the body, and then the gas concentrations out. And the simplest way to measure all these is to flatten the changes, because what's coming out of the mouth is fast changes. And if you push it through a long tube into a big box, you can get the average values, and they represent how the lungs are pulling air in and out, and it represents metabolic function, both calories burned, efficiency, looking at your metabolism versus your power, your speed output, and then looking at even utilization of carbohydrates and fats. So when lab carts came around in the 70s, you didn't have easy access to fast processors that were that small. So instead of trying to do more complicated signal analysis, they simply said, make all the make this big box, make all the trend lines really flat, and then you just take average flow times the average difference in the gases, and that's your VO2.
And I'll just step in, because that idea is taken off of what most people will call the gold standard, which is the Douglas bag. Which, if you've ever seen a picture of a Douglas bag, it is literally a giant bag filled with your exhaled air. And that is still considered the gold standard, which is so ridiculous that it's very similar to being tied to the idea of a lactate value indicating what's happening at the muscular level. It's a slow, methodical process that is fraught with error, but was the only way that they could get it at the time. And everything that has been developed since then is still anchored to that idea that is a gold standard.
Well, what is for you at this point in time, given the technology that we have access to, the tech that you guys have created, what should be the gold standard? What is your gold standard?
I don't think so. I think there's been such rapid change. I don't think there is a gold standard. You can't compare breath by breath analysis to something that used to collect gases into a bag for 20 minutes and then assess what happened to all they could do is say, in that 20 minutes, this is how much oxygen was consumed, this is how much carbon dioxide is left in the bag. We do some mathematical calculations and say, well, over that 20 minutes, that athlete ran 4 miles and this is how much CO2 he blew off. There are so many potential errors in that. And then you compare that to our modern technology where we can actually see what happens at the muscular level, what happens breath to breath. And so I think trying to compare something to a gold standard that doesn't have any relation to the current understanding of physiology doesn't make a whole lot of sense. So there are very good lab carts but they are still having the challenge of having mixed gases from a number of different breaths. Whereas a smaller more portable the unit, the quicker you can pull data. And ours is the only device that pulls it breath by breath right at the source of where the person's breathing out.
And this is essentially,
Go ahead.
in this layout, I think it should be made clear. I don't think we necessarily compete with lab carts. I think they have a great function. They're robust. They're big. Why did we build VO2 Master? For portable, affordable, and simple measurement. All the coaches like Andrew was and is, who needed metabolic analysis without going to a lab and getting a $50,000+ cart. It's pretty inapplicable. So I guess there's 4 categories. There's the Douglas bag, there's lab carts, and then came along backpack units. The Cosmed K5, Cortex Metamax 3BR2. And how do those work? Well, instead of having the flow sensor at the end of this breathing tube, like a lab cart, they just put the flow sensor right on the face. And then in the backpack, there's a small pump and then your gas sensors. So when you exhale, the device turns the pump on and pulls a proportional sample of the air away and then mixes it together and takes the reading. So, lab carts positioned as, they're more accurate because these backpacks can have a lot of error in aligning the flow measurements right here with that delayed gas sample to the backpack. And I think they're right. Tiny shifts in that timing can cause a huge error, since now you're getting the fast changes in breathing. So if you have 2 waveforms doing this and you misalign them by just a few milliseconds, you can actually completely change the output. So I guess what we've made is still a proportional sampling system, but that brilliant engineer Kyle figured out a way to do it off an inherent design of a Venturi. So, the Venturi effect means if you put a certain amount of air through here, you can actually create a proportional pressure difference across a side tube and force air through it. So, without dealing with any kind of timing issues, the Venturi just proportionally samples. So if you're breathing 80 breaths a minute, 70 breaths a minute, that's a 300 or 400 millisecond exhale. And if you had electronics controlling the sampling, you're going to end up with some error. The typical backpack unit has a 3-foot hose on it to pull air from the flow sensor at the front to the gas sensors. And it relies on the electronics to detect the start of the exhale, turn on the sampling pump, sample the air, and stop at the right time before the person starts inhaling. Because say if the pump starts too late, you miss some of the exhale breath. And if it ends too late as well, you actually get ambient air in the sample line, which can totally screw things up. And what we've developed is a inherent passive way of doing that. So, use the Venturi effect to take a tiny proportional sample, inherently truly proportional sample that reduces error, and push it through the same exact type of Nafion tubing to desiccate the air, and then into the oxygen sensor and out. And since the proportion is so much smaller, you don't need a huge tube length to dry the sensors. So now you have no pump, you have tiny tubes, and the oxygen sensors are actually like that big. So all of that fits in one little wing on a Hans Rudolph blue mask, and on the other side you just put a Bluetooth antenna, AAA battery, and a little power button.
You make it sound so simple.
It was really it was hard to build.
It's a funny conversation with people because people they see it and they don't believe either the accuracy of it or the validity of it. And the easiest argument I make is that the oxygen cell sensor that we use is exactly the same oxygen sensor as used by the lab carts and other much more expensive devices. And the method that we use to measure volumes is exactly the same. There's 2 main ways of measuring volumes of air as it moves through a space. And one is with a micro fan, a little tiny fan that circles as you blow through it. You can actually see the fan blowing, and as you suck, it turns around, goes backwards, and it's got some challenges to it because it's got momentum to it. So you have to stop the fan moving and pull it back. But it works.
That's what a spirometer would use. One of those basic spirometers. Yeah.
Absolutely, yeah. So medical grade spirometers use fans, and so did the FitMate, right? Yeah. And the other way of doing it is through a pressure differential and measuring the changes, and that's through a Venturi tube, and that's the other half of our competitors use that. And both of them are valid ways of measuring volumes. And so our device is not the uniqueness and what sets our device separate from those other devices is not the technology around how we sense oxygen and how we measure oxygen and how we measure volumes. It's the only thing that we've done is patented the ability to remove the pump and to be able to send the information Bluetooth. So when Peter was saying that he could build it in a weekend, it was because he pulled the device apart and said, well, it's not rocket science. This has been done for 50 years, how to measure volumes and how to measure oxygen. And the devices are already small enough to do that. What we were missing was the implementation of Bluetooth technology and miniaturizing the pump. And when Kyle Halliday helped us miniaturize the pump, that put the three pieces together. And so it's a funny conversation when they say, well, how accurate is it compared to the Douglas bag? I'm like, oh, way more accurate than a Douglas bag.
If you assume that
was a big leather cow bladder that they would breathe into. So yes, it's like much more accurate than a Douglas bag.
A 110 liter bag where you assume there's no leaks in any valves. They didn't let the gas sit long enough that the condensed water absorbed any of the CO2, and then they attached it to a really slow analyzer that perfectly measured the volume and the gases to give you one number that represented the whole effort. And yeah, is the modern technology better than that? Maybe.